Here are the notes about congruence of integers. We will start with the definition of what it is for two integers to be congruent modulo n. Basically, it means that they have the same remainder when they are divided by n. So, definition, let n be a whole number. Two integers a and b are congruent modulo n if they have the same remainder when divided by n. And it is written like this with this kind of triple equal sign. So it's going to be more clear with a few examples. We will study 9 and 34 and see that they are congruent modulo 5. So when we divide 9 by 5, we get 1 and a remainder of 4. So 9 equals 1 times 5 plus 4. How about 34? 34 divided by 5 equals 6 with a remainder of 4. So 34 equals 6 times 5 plus 4. As we see, for both of them, the remainder is 4. 4 here and 4 here. So it is a fact that you can always do that, and it is important to agree that when we write this like that, the remainder will always be a number between 0 and, in this case, 4. In general, if we divide by n, the remainder will always be a number between 0 and n minus 1. Second example, 20 and negative 8 are congruent modulo 7. So 20 over 7 is 2. And 20 equals 2 times 7 plus the remainder, which is 6. How about negative 8? When we have negative numbers, we need to go far enough that the remainder is a number that is between 0 and n minus 1. So here, in the case of modulo 7, the remainder is going to be a number between 0 and 6. Therefore, negative 8 is equal to negative 14 plus c, plus 6. Again here, since the remainder is 6 for both numbers, they are congruent modulo 7. So if you think about numbers that are congruent, for example, modulo 5, you can see that it's going to come in a cycle. Every 5, it's going to be congruent to these numbers again. For example, 34 and then 39, 44, 49 are all going to be congruent to 34 and congruent to 9 modulo 5. So, in this exercise, we're going to divide and see that the remainder is indeed the same. For 18, 18 over 8 is 2 with a remainder of 2. What about 82? 82 divided by 8 is 10. So 82 can be written 10 times 8 plus 2. The remainder is a number between 0 and 7, and it is the same. So 18 is congruent to 82 modulo 8. For the second example, 5 divided by 9 equals 0 with a remainder of 5. And for negative 13, we need to go far enough, so it's going to be negative 2 times 9, which gives negative 18, and then plus 5 to reach negative 13. So the remainder is 5 in both cases, and therefore it is true that 5 is congruent to negative 13 modulo 9. So the definition we saw until now makes it kind of intuitive how to figure out that two numbers are congruent. You just look at the remainder. The definition above makes it easy to understand the concept of congruency. However, it isn't practical to use in proofs. The result of the following proposition is much more convenient. So when we will have to prove propositions or theorems using congruency, we will prefer this here rather than the intuitive definition. In many texts, including our own textbook, this is given as the definition of congruency. I think it's better to start with the definition being intuitive and then state a proposition and show that it is equivalent to our definition. So definitions, whether we see it or not, are almost always biconditional statements. Two integers a and b are congruent modulo n if and only if n divides a minus b. Even though we never write definitions with if and only if, we talked about that in a previous section, we should. It's just redundant and not a bit clumsy, so we don't. But this is the way we should understand definitions. So we're going to prove that this proposition is true, and after we've proved that it is true, every time we see that a and b are congruent modulo n, we will write this. We won't talk about the remainder being the same. So because it's a biconditional statement, we're going to split it into two, and we will start by showing that two integers a and b are congruent. If two integers a and b are congruent modulo n, then n divides a minus b. So by definition, a and b have the same remainder r when divided by n. And so when we write them, we can say that a is kn plus a certain remainder r, and b is l times n. It's a different multiple of n, but it's the same remainder r. So when we now subtract a and b, a minus b equals kn plus r minus ln plus r, and the r's cancel out, so it's equal to kn minus ln. And if we factorize n, we can see that n minus b is indeed a multiple of n. It's actually k minus l times n. So n divides a minus b. So that was proving the first direction, if this, then that. And now we will prove if this, then that. Secondly, let's show that if n divides a minus b, then a and b are congruent modulo n. And to prove that, we will use contrapositive proof. So we suppose a and b are not congruent modulo n. So this time, it looks a lot like before, but there's a major difference. We're supposing they are not congruent. So a equals kn plus a certain remainder, and b equals ln plus another remainder, and these are different. They are different because we made the hypothesis that a and b are not congruent modulo n. So they have a different remainder. So when we do a minus b, it's the same process as earlier. Kn plus r1 minus ln plus r2 equals kn minus ln plus r1 minus r2. And when we factorize, we get n times k minus l plus r1 minus r2, where r1 minus r2 is not 0. And that entails that n does not divide a minus b. N times k minus l is a certain number, but then there is a certain remainder that is not 0. You may argue here then that r1 minus r2 is not positive. It could happen that it becomes a negative number, but in any case, it's not 0, so it is not going to be divisible by, it's not going to allow n to divide a minus b. So now that we've proved this, we can use this here as a definition of congruency. It's absolutely equivalent to the definition we saw. So 2 examples. First one, let a and b be integers and n a whole number. If a is congruent to b modulo n, then a squared is congruent to b squared modulo n. Given that a is congruent to b modulo n, we know that this means n divides a minus b, and which means a minus b equals c times n for some integer c. The trick here is to multiply by a plus b. We multiply both sides by a plus b, and we get a minus b times a plus b equals cn times a plus b. Why that? Because a minus b times a plus b equals a squared minus b squared, and we can see that a squared minus b squared is a multiple of n, and that means n divides a squared minus b squared. Perfect. That is what we can use as the equivalent to the definition of congruency. Therefore, a squared is congruent to b squared modulo n. A quick notation before we do the last proposition. It's pretty obvious. If two integers a and b are not congruent modulo n, then we write this like that with a bar across the congruency sign. So final proposition, let a and b be integers and n a whole number. If 12a is not congruent to 12b modulo n, then n does not divide 12. When we have something like this, does not divide, it's kind of a hint that we will want to use contrapositive proof, because it will turn it into an n does divide 12, which is much more convenient. So we will use contrapositive proof. Let's assume n divides 12. That means that 12 equals c times n for some integer c. It's kind of interesting here because we're going to look at 12a and we're going to substitute 12. 12 is c times n, and this allows us to write that 12a is a multiple of n, or 12a is divisible by n. We can do the exact same trick with 12b and find that 12b equals cb times n, so it is divisible by n too. Now, since they're both divisible by n, it means their remainder is 0. So in that particular case, it means that 12a is congruent to 12b modulo n. So that completes the contrapositive proof. As an additional note, we can say that indeed 12a is congruent to 0 modulo n, 12b is congruent to 0 modulo n. But that's giving more information than what the proposition said. Okay, so this is it for the notes. Please refer to your checklist to see the other things that you have to do in this section. Thank you.